So we're going to look at an example of a sampling distribution. Well, we're first going to start out with the population. I've got 5 people in my class. That's my population, and I'm looking at grades on a test. So I know what the population mean is and the population standard deviation. The population mean is 69, and the population standard deviation is 8.888. So I know that. Now we're going to look at a sampling distribution of the sample means, where my sample size is 2. What is that? That's every way I can take 2 people from my population of 5, every different combination, and I'm going to calculate the means of each of those 2 people samples. So I take person 1 and 2, their scores were 62 and 80, the mean is 71. I take person 1 and 3, I find the mean of their score. That's where I got the 60. I took the mean of 62 and 58, and so forth. So that I've got the 2 sample means. And what I'm going to do is I'm going to find the mean of those means. And look at that. The mean of those means is 69, the same as the population. Now, is that an accident? Well, I don't know. Let's look at the standard deviation. And here you see me call it standard error. When we see the term standard error, that indicates to us that we're doing a sampling distribution, because the standard error is the standard deviation of a sampling distribution. So the standard error is a little bit less. Let's look at our sampling distribution of the sample means for a sample of 3. Well, when I look at that, I take every way I could take 3 people from the 5, and I calculate the mean of the 3 people sample. So person 1, 2, and 3, their mean is 66.666, a repeating decimal. And I take person 1, 2, and 4, same thing. And I got many decimal places so I won't have rounding error. And when I take the mean of those means for samples of 3, again I see that the mean of those are 69. Unusual. Is this unusual, or was this to be expected? Then look at the standard error. Well, that keeps decreasing. Now we take a look at samples of size 4. So every way I could take 4 people from the 5, I take the mean of those people, and I find their means. Then I take that column and find the mean of those means, and again I see 69, with a standard error less than the one before it. So I'm seeing as my sample size increases, my standard error decreases, but the mean of the means remains the same. And when I do the last one, the sample of 5, of course the mean would be 69, but look at the standard error. It's less. So what's going on here? When we're dealing with the sampling distribution of the sample mean, the way we denote the mean of our sampling distribution is mu sub x bar. And what we find out is that mu sub x bar actually does equal the mean of our population. We saw that in our Excel example. Therefore, we call x bar, we say that x bar is an unbiased estimator for mu, or mu sub. We also find that the standard error, that sigma x bar, the standard deviation of my sampling distribution, equals the population standard deviation divided by the square root of our sample size. That's what n is. So averages are less variable than individual observations. In other words, as my sample size increases, my sampling distribution's variation will decrease. So as you can see, the mean of my sampling distribution, where n is 2, equals the mean of the population. So my mu sub x bar equals mu. And I see that for each of my different sampling distributions where I have different sample sizes. And that 6.2849000225, that's just 8.888194417 divided by the square root of 2. That 5.13 and so forth is just my population standard deviation divided by the square root of 3. So those numbers were by no means just an accident. They are because that's what a sampling distribution gives us. So again, we see that the mean of my sampling distribution equals the mean of the population, and the standard error of my the standard error, or the standard deviation of my sampling distribution, just equals the population standard deviation divided by the square root of n. Now let's see picture-wise what's going on with the distributions here also. The dark line here is the original distribution, and as my sample size increases, my distribution becomes smaller, my variance decreases, and it decreases by the square root of my sample size. So we have less variation for larger sample sizes. So the probability distribution of a statistic is called a sampling distribution. Now we use them to make probability statements about the values the sample mean takes on and the likelihood that our estimates of the population mean based on the sample mean are accurate. Now sampling distributions depend upon the sample size, the population mean, the population standard deviation, and the shape of our population distribution. So again, if we repeat taking simple random samples of a certain size, we call n, from our population and calculate the sample means for each of those samples, the distribution of this accumulation of sample means is the sampling distribution of the sample means. Now something that we must look at that's very important is that the sampling distribution of the sample means does not necessarily look like the population distribution, and we're going to see a very good example of that very soon. Now we're first going to look at an illustration really of the law of large numbers. And then getting into sampling distributions. But first let's take a look at this sample. As you can see, the mean is 2.56. It is right skewed, so it's asymmetric, and there's my population. Now look at these these samples of size 25 from the population. They look somewhat like the parent distribution, but none look exactly like it. They all look a little bit different from each other also. Now let's look what happens when we have a sample of 1,000 from our population, that very right-skewed population. The distribution here looks a lot more like the parent distribution. So the distribution of measurements in a large sample looks like the distribution of the parent population. Again, think about the law of large numbers. Now we're going to look at something a little bit different. We're going to look at sampling distributions taken from that very right-skewed population. So remember, this is our population. It has a mean of 2.56. We're going to do sampling distributions from this distribution. So this is a sampling distribution where my sample sizes are of size 10. Look at that distribution. It does look a little right-skewed, but not majorly. And look, the mean of that distribution is the mean of the population that it came from. Now let's look at if I do a sampling distribution where I have a size 40 sample. So I take sample sizes of size 40 over and over again. Look at that distribution. It's looking very normal. And when I take samples of size 160 and I do that over and over and over again, look at that. That looks extremely normal. And if you look at the mean of both of those are both the same mean as the population. So we see that sampling distributions tend to start looking normal as our sample size increases, even though our parent distribution was highly skewed. And also look how our variance has changed. With the sample size of 160, our variation has decreased quite a bit. So this gives us that the distribution of measurements in a sample look like the distribution of the parent population, not necessarily like the normal curve. And in the sampling distribution of the sample means, they look like normal curves as the sample size increases, even though the parent population was definitely not normal. We also saw as the sample size increases, the sample mean does get closer to the population mean, and even the histograms start looking the same. And then the spread of the histograms in sampling distributions of the sample mean gets smaller as our sample size gets larger. Now this, as our sampling distribution starts looking normal, even though our parent distribution wasn't, is the central limit theorem. It says regardless of the shape of the population distribution, the sampling distribution of the sample means becomes approximately normal as the sample size n increases.